Okay, the title of my talk is to talk about the water budget of Typhoon Nari, and of course this is the Morakot workshop, so I will have give some implication of the water budget for the Typhoon Morakot. And this is a cooperation study between myself and my student, Mr. Chen Sun, and Dr. Scott Brown at the NASA Goddard Space Flight Center. Okay, a lot of people show the simulation track and the observed track of the Typhoon Morakot, and this is what we did for the Morakot case. So basically, the simulated landfall position is from the wharf is on Elan County. Observed landfall point is on Hua-Lian County. So basically, it's slightly to the north. However, the general trend is quite good. And then this shows the comparison of the 24-hour accumulated rainfall on August 7th. So the maximum rainfall is above 1,500 millimeters, and the observed maximum rainfall is about this value. So for the first day, it's over. However, for the second day, the simulated maximum rainfall is also on the southern tip of the Central Mountain Range. Is about 1,250 millimeter rainfall, but the observed rainfall is much more than that. So for the second day simulation, we got less rainfall compared to observation. However, we can see this kind of multiple banded structure as shown. So in terms of radar effectivity, showing this morning by Professor Benjo, Tai Chi, and Chen Yu, the simulated rainfall shows the similar kind of structure. And this one, we like to compare the simulated radar reflectivity fields. But basically, at the time of August 7th, 21 UTC, we can see multiple cellular structure embedded within this rotating principal rain band. And this is of the radar composite. So basically, we can see a good correspondence of the rain band structure here compared to here. However, on the eastern side, the simulation does not capture well. So, but basically, for the main feature here, the cellular structure within the primary rain band is quite well captured by the WRF model. So, if we take a vertical cross section across through this line, cutting through the southern part of the Central Mountain Range, we can see multiple cellular structure here. Color is for reflectivity, and the contour line is for the vertical velocity. And in particular, we can see there are a lot of cloud waters in the low level and some cloud ice field above the melting levels. So basically, we can see in terms of radar reflectivity, the model seems to produce a reasonable simulation. However, we would like to ask a fundamental question. Does the model simulate the right amount of precision based on the right microphysics processes? I think this is a very important question. So in order to answer this question, we need to be more careful about the water budget. So we do a more complete water budget study based on the Typhoon Nari simulation. The reason is because we have more complete data set of the Typhoon Nari simulation. And also we have more complete microphysics output from this simulation. Later we will basically do the same thing of Typhoon Nari, but we will apply it to the Typhoon Morakot later. So this is our simulated track for the Typhoon Nari case. The solid line is the best track analysis from Central Weather Bureau, and the gray line is our simulated track. So basically we can see that even though the landfall point is slightly to the north, but as long as the Nari is over the island, the Taiwan island, the simulated track follow very closely with the observed track. And this one shows the time series of the central zero pressure and the maximum wind speed. So basically, we can see that even though before the landfall, the 2 kilometer MFI seems to be a little bit stronger than the best track analysis. However, after making landfall, the simulation captured quite well about the feeling of the central pressure and the weakness of the maximum wind after landfall, and then remain a roughly constant value after landfall. So this one also shows the maximum, the 3-day accumulated rainfall period from the observation from the rain gauge data. This is from the 6 kilometer MFI result. This is from 2 kilometer MFI result. So basically, we can see the 2 maximum rainfall over the mountain snow here and the RD mountain here are well captured by the model. And as long as when we increase the model resolution from 6 to 2 kilometer, the accumulated rainfall amount is also increased. So we have more confidence about the precision, the results. So we do a careful budget equation. First, we look at the water budget from the QV, and this is we basically follow the methodology of Scott Brown in his JS paper. So we recast the budget calculation in a storm relative framework, in particular in the flux code and flux form. So it's the horizontal flux convergence, vertical flux convergence, and the change of water vapor due to the diversion of the wind alone, and also this condensation, evaporation, and other terms. By the way, this is in a storm relative framework, so that the motion of the typhoon is subtracted already. So C is the total condensation and the deposition. E is the sublimation, the evaporation. So BV is the boundary layer contribution to the water vapor, and dV is the turbulence mixing terms. And we do the same thing for the cloud field. Cloud field, which we mean is the combination of the cloud water and the cloud ice field. So basically, all the terms are here are similar to the water vapor budget here. And then we also do the same thing for the precipitation budget. Here, precipitation, we mean the combination between the raindrop, snowflake, and the gravel. By the way, for the precipitation budget, we have one extra term due to the sedimentation of the falling of hydrometeors. So if we look at during the oceanic stage, basically the typhoon Nari revealed an asymmetric structure. So if we look at more details, if we take this along the cross section, we can see a very deep eye wall and then a primary rain band over here. And then if we look at the horizontal structure of the reflectivity and the wind field at the 40-meter surface and the 3-kilometer surface, 7-kilometer surface, and the 12-kilometer surface, and the color field are all for radar reflectivity. And the low level for this one, the contour is for the radial velocity. We can see a strong negative rate inflow is here, and then here the contour field is the vertical velocity. We can see updraft.